Good. Good morning. And my name is Xiaoming again. I'm an assistant professor in OSU. This is my third year. I want to first thank my colleagues and my students, Roman, Poudyal, Jeffrey Spitler, who's a professor here in OSU, and Matt Mitchell is his student who helped us a lot in the experiment. So I'm going to talk about something called a geothermal heat exchange pile, or some people call it energy pile. The basic idea is to combine the vertical loop of a ground source heat pump system with the pile foundation of a building so that we can offset the drilling cost of installation of vertical loops. It's not really a new idea actually. This kind of pile has been built in Europe for maybe 10, 15 years. There are thousands of piles already constructed already. In America, this is still at the very beginning. I don't think there are probably a few design companies who has ever designed an energy pile, and maybe a few or even a couple contractors who has ever constructed an energy pile. So there are some concern both on the heat exchange side and on the foundation side about this kind of idea. So we want to do a kind of proof of concept actually. There's something new that we did in this research is that we built a large diameter pile. The large diameter, I mean, it's about 1 meter, a little more than 1 meter diameter. It's not so large in terms of a pile, but very large in terms of a vertical loop. We are actually, from the literature search, we are actually the second largest in the world in terms of diameter of the pile. We have only heard about in Japan, they built something about 1.5 meter diameter, but we didn't see any publication from that. With this diameter of a pile, we can put 8 vertical loops in the pile. So that's something new. We want to see how this pile is going to function in terms of heat exchange and also on the foundation's behavior. All right, let's start the next. All right. I think I will look stupid if I talk about green energy and global warming over here because you guys know it much better than me. So I just have one slide about my understanding about the ground source heat pump system is that you can have a ground source heat pump and sort of transfer the heat from the building to either extract heat from the ground or inject heat to the ground by either horizontal loops or vertical loops. The concept is that because the temperature in the ground kind of goes about constant over the year after 50 feet. And even the 30 feet only varies about a couple degrees in terms of winter and summer. And this temperature range is the typical range of temperature variation on the ground surface in the middle of America, somewhere near Kansas or Oklahoma. Okay. So since many of the larger buildings are already supported by piles, and those piles goes into the ground to some depths. Some are shorter, some are longer, depends on the size of the building. The idea, can we combine the vertical loop or build a vertical loop into these piles so that, because anyway we're going to drill into the ground, then why don't we build a vertical loops over there so that to offset some drilling cost of building more vertical loops beside the building. Of course, this only applies to a new building, not the existing building. Okay. The question is, what's the efficiency of the energy pile or ground source or the geothermal heat exchange pile, and and how it compared to the vertical loops or horizontal loop system. And is there any damaging effect to the foundation? I mean, is that going to affect the load capacity of the foundation or the settlement of the building? So that's the question that we have before we do this research, and we want to prove it. Just a little bit about what is pile. Usually when you have a larger building that has a larger load, they will be supported by a number of piles. A pile is basically a cylinder or something that is long in the length and smaller diameter, and transfer the load of the building to some good soil or bedrock below the ground. A pile supports the vertical load of the building by both the side friction from between the pile and the soil and the base resistance. And depending on the size of the pile, QS and QB stand for side friction and base resistance. QS can be larger and QB can be larger, but the sum of these two should be equal to the load L. And that's how the pile support the load of a building.
Is a pile forced into the ground, or I guess it may be drilled into the ground?
Right, there are two kinds of piles that we can build a pile, two kinds of ways we can build a pile. First is we made a pile in a factory, what we call a precast concrete pile, and then we sort of hammer it into the ground. Mm-hmm. And the other way is to drill a hole and pour concrete and then form a pile in the ground. There are advantages and disadvantages of both of these. These we can do a better quality control of the pile because we can look at it, but it's going to be more noisy. It's possible, if we are building larger piles, possible to break the pile during the hammering process. This hammering is not an issue. It's a low noise technique, and but the inspection is difficult. You can't see the pile. After you pour concrete, you need to make sure there's no voids in it, which is hard, based on some experience. But the pile I used over here is a cast-in-place pile. Actually, you can build a vertical loop into precast or the cast-in-place pile. We just didn't do this because the association that donate our pile is from the drill shaft association. They only do this kind of pile. And they can build larger diameter piles, because with this, if you go larger diameter, like 1 meter, it's hard to hammer it in the ground, especially if you want to penetrate rock. Now, again, the idea of an energy pile or geothermal heat exchange pile is to combine a pile foundation, a deep foundation, with a vertical loop. Then we have an energy pile. And we can put several of these underneath the building to be part of the ground source heat pump system. And usually when you look at the ground source vertical loop system, it looks like this. I learned this from the mechanical engineering people. They use the red color and the blue color for cold and heat. And most of other people, they did their research on a single loop geothermal exchange pile, which looks like this with a smaller diameter. And there are some research going right now in America too. What we looked at is a larger diameter pile that we can put multiple loops into it, because we want to maximize the benefit of those vertical loops. That's why we put them far away from each other to the outside of the pile. But we need some cover thickness to protect the steel reinforcement. So those loops are tied to the steel cage of the pile. The objective is to see what's the thermomechanical coupled behavior of a larger diameter energy pile with multiple vertical loops in it. So let's see some pictures about our field test. Again, I want to thank the support of IGSHPA. I actually spent a lot of time at the beginning just trying to find a place to build a pile. And I know there's a place on the northwest side of the campus, kind of a very strange place. That place is it's a gated area, right? It looks like a abandoned facility, and it's gated area. There are maybe 7 or 8 locks over there, so each lock may represent a different office, and they can get into it. And when I talk to different people, everybody is saying, yes, this is my place, don't touch it. Right. But when I ask who should I talk to get a key, and they were saying, no, I don't know. I don't know who you should talk to. And finally, our department head, John Winstra, he suggested me to talk to Jim Bose in IGSHPA. And Jim he's a very nice guy. He just, oh yes, this is our interest. We're interested in this. And just go ahead to build it over here. And then the next day, Steve Stephens contacted me, and we go to there, and we find a spot. It's right, I don't have a smaller zoomed in map, but it's sort of, there are 2 smaller buildings over there. Our pile is right over here. It's right over here. We just have 1 single pile. And this is where we are right now. Actually, I didn't know IGSHPA is over here just last week. I know it's somewhere in Stillwater. It's actually very close to my house. So I walk my daughter a lot near this lake. So we see this building all the time. I didn't know this is IGSHPA. Anyway, so first thing what we do, I'm a geotech people, so I do any research, I will go to explore what's the soil underneath the site in the ground. So we find a company who are willing to do this for us for free, and they basically drill 50 feet into the ground and then figured out how many layers of soils are there and what's the soil in each layer. And we did some laboratory tests and some in situ tests over here to figure out what's the mechanical properties and some physical properties of the pile. So on this side, there's a surface clay up about 10 feet, and underneath that it's weathered shale, weathered to different levels. So some thickness may be very strong and some are weak. Once you penetrate a strong layer, you may find a weak layer, then another strong layer again. So it's kind of all the 40 feet over here are weathered rock. We didn't hit a good load-bearing rock at the bottom actually, but we stop over here because we want to build a pile of about 40 feet long. We decided we actually can go further. We should have gone further actually, but at the time we decided this is enough, and this is a kind of an average size of a drill shaft in Oklahoma. So that's why we decided to build a 40 feet long pile. And here is how the reinforcement cage look like. If you see the black pipes over here, those are for vertical loops. So first day of construction, we have this steel cage shipped to the side, and we just tie the vertical loops onto the side of the cage. And the way we set it up is that we have 8 loops actually, but we use 2 of them over here as input, sort of a series of 4 loops over here and 4 loops over there, and they're parallel to each other. And we can try different setup actually. It's very interesting to me, but we just haven't done much trial yet. Now another thing we did on the cage is that we put a center bar in the cage. We sort of put 8 strain gauges which can measure both actual strain and the temperature at the same time. We put them relatively equal spacing to each other, so they are about 5 feet spacing. It's a 40 feet long pile. Then the next day, the driller came in and drilled a hole for us, and then we sent this instrumented steel cage into the hole, and then we pour concrete to form a pile. That's how it is constructed. I want to show some more pictures. This is a hole, how it looks like, and this is how they pour the concrete. We need to protect the cables that come out from the sensors. Actually, putting concrete is just a one-man work, and we sort of have 3 inspectors over here just talking. And, it's very easy work, actually. I was surprised. And eventually, we filled up the hole with concrete, and at the end, we just need to sort of organize the loop so that we remember which 2 are actually together. And so we make sure one in, one out. So that's this guy is doing over here, and this guy is trying to use some vibrating thing to get the air bubbles out from the concrete.
Did he do that from the bottom to the top, or is it just at the top?
Actually, from the bottom to the top. Every maybe a few feet, they just stick that thing in and vibrate. Yeah. So this is eventually how the pile looks like. After that, we covered it so that nobody actually drops into it, and also to help to cure the concrete so that there's no crack forming. And we waited a couple months for the temperature to become stable, and we start to connect the vertical loops to a trailer that Dr. Spitler student built for the thermal response test. So we need to connect the vertical loops to the trailer with some flexible pipes, and we make this kind of series and parallel connection with the flexible pipes. Then Dr. Spitler is very careful about research, so even though this is not funded by any agency, he put his own money to insulate all the pipes outside the ground. And we actually built actually not a build, we bought a shutter from Lowe's to cover it so that we can get a more reliable test result. Here's the trailer that Dr. Spitler's students built. So these the pipes connect to the trailer, and we are ready to run the geothermal response test, the thermal response test. And here is, I don't know much detail about how this test is, how the trailer works and how the test is done. But here the trailer looks like. Some summary, the test, because this is a large pile, so the test actually takes 39 days to finish. I mean, for the temperature to start to become constant. And we control the flow rate, we can control the heat supply during the test, and what we measure is the water temperature that goes into the pile, and it's initial fluid temperature and final temperature of the fluid that goes through all the system. And pile center temperature, which should be close to this, which really is at the beginning of the test. This is about the average temperature in the ground. And eventually, when we did a heating test, actually, by the way, the temperature, by pumping the hot water into the pile, the temperature eventually after the test becomes 35 degrees in the pile, not the fluid. So it's a little lower than the fluid temperature. And this slide basically shows that we control the heat injection level and the fluid flow level. So they are about to the target of our goal, with a small variation, of course. And then we can measure the temperature of the water, inlet temperature, outlet temperature, and the mean temperature throughout the 39 days of testing. So the temperature of the system actually goes up and kind of go more stable at the end of the test. And we can also measure the temperature from the strain gauges that we install so that we can get a temperature profile of the pile along, sorry about the SI unit over here because this is a student's thesis. So he wants to put an SI unit. So this is actually 40 feet. We can see the temperature along the pile during the test at this is 0 day, this is actually temperature increase, 15 degree, 20 something degree at different days. And the temperature of the pile is kind of a little uniform at along the pile, but dropped a little bit just below at the bottom of the pile. It might be because there are more surface area at the bottom, so it's going to be affected by the soil a little more. And the strain gauge can also measure the thermal strain of the pile. This is how the strain looks like. And from this, why we measure this is we can figure out how the load transfers through the pile. And the analysis part, we are still under the process of trying to see how we can look at the data, and we got pretty much all fixed in the mechanical side, but on the thermal side we are still working on it. One thing we did is that this is for foundation design, that we can use a modified TZ model, which is I'm sorry to show you the equations over here, but what we want to do is to figure out how the load transfer inside the pile, I mean from the side friction and the bottom resistance. So we can isolate the pile into small blocks. This is like a finite difference method. And each block is related to the soil by a spring that we assume the friction of the pile is sort of linear proportional to the displacement of the pile at each location. Okay. But anyway, the TZ model is not something we created, that's pile foundation design people created. What we did is put a thermal component in some of the equations so that we can take care of the temperature change and the expansion and contraction of the pile from the temperature change.
Was there ever a load put on the pile? Vertical load?
No. The pile, originally we tried to put some load, but with several hundred tons of load, that's going to be a huge pile of concrete or something. Mm-hmm. We just do not have enough funding to put that load. That's something that the pile is still there. We can do maybe in the future. It will cost us, say, about at least $20,000 to $40,000 of money. I just do not have that money. So the student put those equations into a spreadsheet, and he can match the strain gauge data by changing some soil parameters. And we did that. We used one temperature at +5 degree temperature, and use it to calibrate those soil parameters. And here are some of the parameters he calibrated, and then using the same parameter, he can match the strain distribution along the pile at all other different temperatures. So we think we made a pretty good job in terms of understanding how the load transfer through the pile when the temperature of the pile changed. And then he ran some parametric analysis. This is to make his thesis a little thicker. So without putting a lot of money. So with a free head pile, what we call free head pile is what we have right now. We don't have any load on top of the pile, which is not the real case actually. But if you change temperature, you increase the temperature and decrease the temperature, you will see the axial force distribution in the pile change. It will put plus or minus a couple hundred kilonewton of load on the concrete. So that's something that pile design people need to worry about, whether this additional load is gonna exceed the concrete strength or not. And we can, with our model, we can analyze that. And we also sort of, in a computer, we simulate a loaded pile. And we load it to 4 meganewton on the top of the pile, which is about 1/3 of the estimated capacity of the pile. Basically, we simulate a pile that has a factor of safety of 3, which is a typical application. So if we load 4 meganewton of load on the top, several hundred tons, and with temperature change plus or minus 10, 30 degrees, and you will see the axial force along the pile. Now it changed, but does not change like dramatically like this. It will affect the axial force distribution a little bit, but not much in terms of this pile. But the big deal is that we can do this kind of analysis in the pile design with the model that the student created. And another thing we worry about is the settlement of the pile foundation. Settlement is basically the deflection of the pile on the surface. We are worrying during the winter and summer, this pile is doing heating and cooling for the building, and the pile surface may drop down and come up, drop down, come up, doing something like this, which is not so good for the structure. The wall may crack if the settlement or differential settlement between different piles, they become a little large, then the wall may crack. So we can actually analyze that with different top load at different temperature. We can simulate this pile. Kind of simulation result is it will go up and down. The top deflection may go up and down for the range of a few millimeter. Now this pile, this size of pile is typically designed for a 1/4 inch settlement, which is a 12 millimeter. So this range of variation is something that we should worry about in a pile design point of view, because with the, say, 5 millimeter change, that settlement may exceed the design settlement limit of the pile. But we can, again, we can simulate that with the model. This is the mechanical part of the test result. I think we have a pretty good hold of it. The thermal part, we are still struggling to look at the data. Basically, what we have is simply a curve of fluid temperature with hours. And there is a simple model which is created by this guy. And the model is actually for a single vertical loop in a uniform soil, which really should not be applied over here. But we sort of apply that model, the equations like this over here, to calculate the thermal conductivity of the soil. What we get is some number like this. This might be an average value of clay and shale, but there's other effects, like there are 8 loops over there. We just do not know any model that can do some analysis on that. We actually need some help at looking at this curve and how. So we have a thermal response test result like this, but how is it compared to a single loop or 8 isolated vertical loops? How they compare to each other, so that we can understand the difference between the geothermal pile with a single vertical loop. Then we can put this in the design, and in the building design, we can, in the future, maybe if we have the ideal model, we can figure out how many piles need to be geothermal pile, or should we put more piles as geothermal pile. So the thermal part, we still need to look more into this. But the number we got is like this. I don't think it's a real thermal conductivity of the soil. Maybe the average, the typical range we just put over here of clay. It depends on the moisture content of clay. Maybe somewhere over here. And for shale, it's a little larger variation. So what we got is not so far from the typical number of clay or shale. And that's all I have so far in this research. And our conclusion so far is we developed a model that can sort of simulate the thermomechanical behavior of, in terms of pile foundation design of an energy pile. And the change for this pile, the thermal load does not change the actual force distribution in the pile a lot. But maybe in other piles, it may be a lot, but we can simulate that. The heating process in the pile will mobilize more axial force or load capacity of pile, but it helps to reduce the settlement actually. And the cooling part increase the set because the pile now shrink because of the cooling. The cooling load will decrease the actual force, which helps the load capacity, but increase the possibility of too much settlement. So which is a very interesting thing we find. For the future, if we are still working on that, we can, if we do not have any more funding, we can keep looking at our current data and develop some analysis. Sort of in the future, we can figure out how, what's the efficiency of a geothermal pile in terms of heat exchange. And we can use computer model to simulate what's the best loop number or configuration. Should we put 8 loops all in series, or in 2 series that parallel to each other, or in 4 series? We can simulate all of that with our some other software that we have. We have a lot of simplification in the TZ model that we have so far. For example, we assume the linear response of between the soil and the pile, but we can look at the nonlinearity in the future. And another thing we want to look at is cooling, and with a loaded test, if we have some funding, we can do a cooling test, we can do a loaded pile test, and also we can do what's the cyclic behavior of the pile when we do heating, cooling, and that's something that I'm really interested to look at, but it will take a long time too, because one test 39 days and heating, cooling. We're trying to simulate 15 years. That's it. That will take a couple of years to finish that. And the last, I want to thank all the supporters of this research. Oklahoma State University provided startup funding, IGSHPA, of course, and the Red Rock Construction, they help us to drill the site exploration hole, and the Spencer Enterprise, they are the driller company. They help us to build a pile, and Professor Ganyo again from Virginia Tech, he helped us on the research a lot, provide a lot of good ideas.